So this section is about something that we call linear correlation. And the one thing you really need to see in the word linear correlation, or the important part of the word linear correlation, is the line. And we're going to get back to that in 1 second. Now, if we talk about correlation in general, a correlation exists between two variables when one variable is somehow associated with the values of another variable. So we can have any type of correlation that we can imagine in terms of different algebraic functions. When we talk about this idea of linear correlation, this linear, we're specifically looking about how closely do the ordered pairs in these two variables resemble a line if we plot them. Can they be fairly well approximated by a straight line? If you have two ordered pairs that can be fairly well approximated by a straight line, then we say that these two variables have a linear correlation. There's a line that you can use to correlate these two variables. So the way that we measure the strength of a linear correlation between two variables in a sample is what we call R. So let's talk for a few minutes about R and some of its properties, and then we're going to take a look at a handful of examples to see if you can get an idea as to how you can approximate the linear correlation coefficient. Okay, so R is what we call the linear correlation coefficient, and it's also known as the Pearson product moment correlation coefficient. That's a mouthful. So instead of calling it the Pearson product moment correlation coefficient, oftentimes we just call it R. And the reason it's called Pearson is because the gentleman that developed it, his name was Carl Pearson, so we do that in honor of him. So again, we're not going to use the word Pearson product moment correlation coefficient. It's just much easier to say what's your R if you're looking at a bunch of ordered pairs and you want to know how linearly correlated they are. So here's some properties that R has. When we measure linear association, we say that a linear relationship is strong if the points lie close to a straight line. So that is if you have a bunch of ordered pairs, and if it looks like you could form a pretty good line from those ordered pairs, then we say that it is a strong linear relationship between two variables. And weak if they're widely scattered about a line. So if you see a bunch of ordered pairs which doesn't look anything like a line, then we say that there's a weak correlation. And the following facts about R help us further interpret the strength of the linear relationship. So one thing we need to know, R is always a number between -1 and 1. So R will always be a number that's between -1 and 1. R is greater than 0, which means there's a positive association. So all of those values for R that are in between 0 and 1, I shouldn't say greater than or equal to 0, sorry about that, I should say this. All of those values for R that are greater than 0 but less than or equal to 1 means that there's a positive correlation. We're going to talk more about that in a second. What do we mean if we say that there's a positive correlation between two variables? And if R is in between -1 and 0, so that is if R is greater than or equal to -1 but less than 0, then we say that there is a negative correlation. Values of R near 0, so if R is equal to 0, there's absolutely no linear correlation whatsoever. And even close to 0, values for R that are close to 0, then we say that there's a very weak linear relationship between them. If R is equal to 0, then we say that there is no linear correlation. The strength of the linear relationship increases as R moves away from 0 toward -1 or 1. So what does that mean? Let's put this on a scale and make sure that you understand what that means. Here we go. So we're going to start the scale at -1. We're going to stop here at 0, and then we'll up that scale to +1. So if R is equal to -1, or if R is equal to +1, these are perfect linear relationships. Okay, so perfect linear relationships from -1 if R is equal to -1 and if R is equal to +1. Perfect linear relationships. And again, we'll talk more about what that means in a second. Now, as R gets closer to 0, the less and less linear they are. So if you have a linear correlation coefficient of R is equal to 0.94, and if you're comparing that with R is equal to 0.03, and if you're comparing that with R is equal to -0.89, let's just make sure you understand which one of these have good linear relationships or strong linear relationships. If you're close to 1 or -1, you have strong linear relationships. Here, strong linear relationships. Think about it in terms of being money. 94 cents is kind of close to $1. Now, what about R is equal to 0.03? Well, 0.033 cents is pretty close to not having any money in your pocket, so it's pretty close to 0. So there's pretty much no type of linear relationship if R is equal to 0.03. R is equal to -0.89. That's a fairly strong linear relationship because -0.89 is fairly close to -1. So these two we would say are fairly strong in terms of having a strong linear relationship. And this guy over here is not so strong at all. There's pretty much no linear relationship if R is equal to 0.03. So the strength of the linear relationship increases as R moves away from 0, closer to +1 and -1. Now the extreme values of R equals -1 and R equals 1, again, that means you have a perfect linear relationship, and that occurs only in the case of a perfect line. So what that means is all of these ordered pairs line up perfectly and you can draw one line through them. Now, something to keep in mind as well is that R is very sensitive to outliers. So that means that if you have a bunch of ordered pairs that look really linear, and then you have this one little wonky ordered pair here, that is going to throw everything off. So if you get rid of that ordered pair, then it looks like you have almost perfect linear correlation. If you put that ordered pair back in, that's going to throw R off. That's going to move you pretty far away from +1. It's going to move you much closer to 0. All right, so this is the part I think where most people really start understanding exactly what it is that we're talking about here. Sorry, let me move, here we go. Now, what I did for you is I pulled up a bunch of pictures because I really wanted you to understand these different values for R and how they work and how they operate. And let's take a look at this first example here. Now, one thing you should notice is that anytime you have a negative R, that means you have a negative slope. Okay, so if you have a negative correlation coefficient, that means you have a negative slope. Remember that negative slopes will fall from left to right. So if you have a bunch of ordered pairs, and if those ordered pairs fall from left to right, if they decrease from left to right, like this guy does over here, that means your correlation coefficient is going to be negative. If you have a bunch of ordered pairs, and if they increase from left to right, like this guy does, so that means we have a positive slope. That's the same thing as saying that we have a positive linear correlation coefficient. Okay, so negative R's just mean a negative slope. Positive R's just means a positive slope. So it's giving us two pieces of information. If your R value is negative, then that means you're going to have a negative slope. If your R value is -1, that means you have exact linear correlation, right? And look, I can draw one line through all of these points here, and it's a negative slope. So remember, positive slopes are going to rise from left to right or increase from left to right. Okay, so -1, negative slope, we have one line that can fit through all the ordered pairs. +1, positive slope, we have one line that can fit through all of the ordered pairs. Now let's take a look at these guys. This guy says R equals -0.94. If you take a look, these ordered pairs, you cannot draw one line that's going to hit all the points on here, but most of the points are fairly close to that line. So you can see we have a strong, we don't have a perfect linear correlation like we did over here, but we have a strong linear correlation. and the exact value for this correlation coefficient is negative 0.94. Same thing if we look at this underneath it. Notice that if you were to describe the trend of these ordered pairs, you would say that these guys are going up and to the right. Now, there is no one line that can hit all of these ordered pairs. And notice these guys are a little bit closer to that one line that we just drew, and these are a little more scattered, so it's not going to have as strong as a linear correlation coefficient as the one above it. But it's going up and to the right, so that means the correlation coefficient is going to be positive. Notice as well that the ordered pairs aren't scattered as tightly around the line, which is why this correlation coefficient, 0.85, isn't as strong as this correlation coefficient is, negative 0.94. Okay, now let's take a look at these guys. This example over here, r equals 0, this is not linear at all, right? I mean, take a look at this. This is a semicircle, so there is no linear relationship between these ordered pairs here. So that's why it gets an r equals 0. Similarly to this guy over here, r equals 0.08, there's pretty much no linear relationship between these points. It looks like a cloud. If you wanted to describe the cloud, you could say the cloud is kind of going up and to the right. That's why we said it's positive 0.08. But again, there's pretty much no linear relationship in these ordered pairs over here. Just to give you a few more examples, take a look at these and see if you can approximate a linear correlation or the correlation coefficient for these examples. So the first thing you do when you look at this guy is you say, okay, this guy is going up and to the right. So that means the correlation coefficient is going to be positive. Not only is the correlation coefficient going to be positive, most of these ordered pairs are on that line. A few of them are off of it. So, but it's pretty darn close. So I would say a good approximation of this would be positive 0.98. Right? I could probably redraw that line again so to give you a better idea really as to what it should look like. Let's see. There we go. Right, and in this case, if the line was perfectly straight, you would see maybe 2 or 3 of the points wouldn't be on there, but that has a strong linear relationship. So this guy also has a positive linear correlation coefficient, right? Because you can see that the cloud-like structure is going up and to the right, so it's a positive slope. But, and this is approximately equal to, but it's not as strong as the one before it. We would say that this has a linear relationship, but it's a weak one. It's not as strong as the one over there. So if we were to approximate the correlation coefficient, I would say a good approximation would be 0.78. None. If you take a look at this guy, this really, it looks like a cloud. You can't tell, is the cloud going up? Is the cloud going down? So a good approximation for the linear correlation coefficient here would be 0. Same thing with this guy. If you see, you could probably use more if you learned about this, great, and if you didn't, don't worry about it. A good approximate, you would be more likely to use a parabola to model this, to model these ordered pairs over here than a line. It's not at all linear. It's a nonlinear relationship. So the difference between no linear relationship, nonlinear means you could use something other than a line to organize it. In this case, like I said, like a parabola. No linear relationship means you really can't use another function to organize this data over here or to approximate that data. Let's take a look at this example over here. What is a good correlation coefficient that we could use for this? Now, I want you to notice this first. Notice that the slope of this line is negative. These ordered pairs have a trend that's going down and to the left. It's fairly close. There are a few points that aren't on that line. So a good approximation for this is r is equal to negative 0.90. That would be a good approximation for it. It has to be negative because, again, notice there's a negative slope. From left to right, we're decreasing. So r is approximately equal to negative 0.90 would be a good approximation for these ordered pairs. Okay, let's take a look at 1, 2, 3, 4, 5, 6 more examples. I encourage you just to pause the video now, look at these and see if you can come up with an approximate linear correlation coefficient for each one of these. And then when you're done pausing the video, we'll come back and go over with what I think is a good approximation for a correlation coefficient for these guys. Okay, welcome back. Just looking at these, I want to make sure you know which ones are positive and which ones are negative. This is positive, right? It's going up from left to right. Same thing, this is positive. Same thing, this is positive. This would have a negative correlation coefficient, right? Because this is going down from left to right. And then we'll talk about these two. Notice this is a scattered cloud. So that would have no correlation. So we would say it's 0. Same thing here. We could use a quadratic or a parabola here to model this, but it's not at all linear. So non-linear correlation. So R is equal to 0. Well, let's come up with some good approximations. Notice this guy, you can draw one line through all of these points. That means there's perfect positive linear correlation. And here R is equal to +1. Anytime you see perfect linear correlation, that there's one line you can draw through all of those points, it's either going to be +1 or -1 if the slope is negative. Here, same thing. There's fairly strong linear correlation, not one perfect. There isn't one line that's going to cover all those points, but it's still fairly strong. So I would say a good approximation for that would be R is equal to +0.92. This guy, we can tell that there's a trend for these ordered pairs, but going up and to the right. So a good approximation for this would be R is equal to let's say 0.71. Now this guy, notice this guy's going down like this, right? But notice that these points are kind of scattered the same way as these points are. The differences between these two is this is a positive slope, so our correlation coefficient is going to be positive. This has a negative slope, so our correlation coefficient is going to be negative. So I would call that R is approximately equal to -0.71. Now what I wanted to do is I wanted to finish with an example of you feeling comfortable approximating, hold on one second, approximating some of the ordered pairs in this graph over here, and approximating the correlation coefficient, and then seeing if you could come up with a situation or scenario that would best explain this graph. So let's see what's going on in this graph. We're looking at now defining the horizontal axes, and the horizontal axis deals with temperature, and the vertical axis deals with sales. So what this is telling us is as temperature increases, right, and notice it's in degrees Celsius too. Some of you will be happy about that, some of you won't care. But as temperature increases, right, so temperature is getting bigger, sales are increasing as well. So as one variable rises, the other variable rises as well. So that means, if you take a look at this, that we have a positive slope. And having a positive slope, it's rising from the left to right, also means that we're going to have a positive correlation coefficient. So let's come up with a good approximation for it. So in regards to a line, I can kind of draw a line. Oh, that's not a bad line to represent all that material. If you take a look, or to represent all those ordered pairs, this line, some of the points go through it, some of the points are a little bit off here, some of the ordered pairs are a little bit off. So a good approximation for the correlation coefficient here would be something like 0.9. Well, that guy's kind of far away. I would call it 0.92. Now, that's pretty specific, but if you say anything, I would be comfortable with you saying anything between 0.85 and 0.98. Assuming that you got within this range, you should feel fairly happy that you're picking up this topic of what it means to have a correlation coefficient. Now let's see, it says look at the graph and see if you can determine what situation or scenario the graph could apply to. So I want you to think about what situation or scenarios happen when the temperature increases and when sales of something increase as well. Well, let's see. My first thought when I looked at this graph was ice cream, right? As it gets warmer outside, we know that sales of ice cream go up. Another example could be bathing suits. As it gets warmer outside, bathing suit sales go up. Another example could be water ice or ices. As the temperature increases, more people tend towards buying cold things. Right, so the few things that I want to make sure you're comfortable with before you leave here is the following, that R is a value that will always be between -1 and 1. Perfect linear correlation occurs at -1 and 1. No linear correlation occurs when r is equal to 0. No linear can mean a cloud, or it can mean another function. So like an absolute value function, or a cubic function, or a quadratic function, which is the same thing as a parabola. So it could be a cloud or something else. But there's an obvious nonlinear trend that's associated with that. Now, having r equal -1 and +1 doesn't occur so often in the real world. Normally, r will take on any one of those continuous values between -1 and 1. But it is possible for you to have exact linear correlation, just doesn't happen so much in the real world in regards to data. Remember that if r is positive, that means we have a positive slope. That means from left to right, our graph is increasing. If r is negative, that means we have a negative slope. That means from left to right, the graph is decreasing. So the graph goes down from left to right versus up. All right, and with practice, if you look at more and more pictures, you'll be able to get a good idea as to how to approximate Pearson's product moment correlation coefficient, also known as